Hello again. This is the last lecture on magnetism. So this is the third part of the lecture on magnetism. So I'm going to start from where I left out last time. So I'm going to start talking about ferromagnetism. So first we'll talk a little bit about the temperature dependence of ferromagnetism. So we know ferromagnetism is a result of this interaction of atomic moments, right? So magnetic moments. So each magnetic moment interacts with other magnetic moments in the material. So this is more like a coupling of spins. So that's the reason why we have ferromagnetism. So we know at room temperature this exchange energy is much greater than the energy due to that randomization due to thermal effect. So thermal energy we call KBT, right? So at room temperature your KBT is small, so then the exchange energy is much greater than that thermal KBT energy. So but if your temperature is very high compared to the exchange energy, so then the thermal energy will exceed that coupling or exchange energy, so that will break down the coupling between spins or among all the spins. So then the ferromagnet will behave like a paramagnet. So this temperature is depending on the material properties. So the temperature over which the ferromagnet becomes paramagnetic for ferromagnets is called Curie temperature. So in the case of antiferromagnet, the temperature is called the Niels temperature. So if you look at the this susceptibility as a function of time, we know for paramagnets the Curie law says kappa goes like 1 over C over T, right? But in the case of ferromagnets, so we don't have strong temperature dependence until we reach that Curie temperature in the case of ferromagnets. So then above that Curie temperature, so it behaves like a paramagnet. So then it will have this C over T, 1 over T dependence like this. You can see the difference between paramagnet and a ferromagnet. So this is one way to identify whether it's a paramagnet or ferromagnet. So when you talk about this ferromagnet in terms of exchange energy and associated Curie temperature, so we start with the paramagnet that has N atoms or ions, each has spin S. So suppose there is some local interaction that actually kind of behaves like having a local magnetic field. So we call it a Weiss field, so or the exchange field. So that more like we are thinking about having this magnetic domains. So each domain has some preferable direction of magnetization. So, but they are not the same direction. But in a given domain, you have alignment of spins. Like here, you have vertically down. So then this is horizontal. So, but each grain has organized magnetic moment. But under magnetic field, so this all the magnetic spins are going to align in that along the magnetic field direction. That's why even if you remove your magnetic field, so still inside these magnetic domains they have permanent magnetization. So that local field we are talking about like having some effective magnetic field. So that exchange magnetic field or the Weiss field, we can approximate in the mean field point of view as some constant times your magnetization. That is the Weiss field. So this is not an external field. This is like some local field due to that exchange interactions. So now if you think about paramagnetic phase, right? Then we have this applied magnetic field BA. So then we can calculate the total magnetization M given by this chi over mu 0, then this applied magnetic field plus your exchange field. That's the total magnetization. But we need to calculate the effective magnetization, the susceptibility. So that is given by M over this applied field, right? So to do that one, so we can kind of simplify this equation. So then we can bring BA to one side and BE M to other side. So you can see here, if I write chi as under Curie's law C over T. So then from this equation you can see your M, if I substitute BE as lambda M, right? So that's the mean field approximation. So then you have common M for this 1 minus this, you have lambda M coming here. So that's what we have here. So then if you calculate that effective susceptibility, that is M over BA, that's how we define, right? Due to the applied magnetic field. So that is given by C over T minus C lambda. If I apply this chi here, this value is C over T. So, but this is, remember, this is different. This is the effective chi. So if you manipulate this one, you get this is CO T minus C lambda. So then I can write C lambda as T Curie. So then this T Curie is lambda is T Curie over C, but we know that C from the Curie law, that is given by this KB over Ng squared J plus 1 mu B squared. But in this case, if you consider J as S, because if we have magnetic this spin magnetic moment L as 0, so then J becomes S, right? So that was simple situation. So now you can see your susceptibility goes like C divided by T minus T Curie. That is for the ferromagnet. So, but for the paramagnets, that is, chi is given by simple C over T. You can see the difference here. So if you look at this equation, lambda given by this T Curie over C, so that is this value. So if you assume S to be 1, so typically if you have like two spins, like in iron or something, you have two up spins, so that means you have half plus half, S is 1. So if you put this equation, typically this Curie temperature for iron is about 1000 Kelvin. So we know G value is 2. If you substitute that one, you get about lambda is about 5000. So now remember your Weiss field is given by lambda times M. So lambda is like 5000. If you take your M is total number of magnetic moments per unit volume, right? So if that value is about 1700, we are talking about this BE, like a very large magnetic field, about 1000 Tesla. So typically, if you talk about this magnetic field due to this simple near neighbor interaction, they are only like 1/10 of Tesla. So that means this BE is not really an applied magnetic field, but that something large magnetic field acting like external field, but that's not an external field. That's a local field, but you can think as a applied field due to these exchange interactions. So if you go further, we can actually model this spin-spin interaction, right? That's the basic idea of ferromagnetism. So that actually, this interaction is a quantum mechanical phenomena. So if you have these two spins with two ions, I and J, so if they have spins Si and Sj, so this actually Heisenberg came up with this exchange energy U given by minus 2J, this Si dot Sj, these are vectors, right? So this J is called the exchange integral or the coupling constant. So if J is positive, that means we are talking about ferromagnetism. If J is negative, that's the anti-ferromagnetism. So this is basically the Heisenberg model for spins. So also we know the exchange interaction depends on the spin orientation, right? If you have two spins, we know they cannot be same direction according to Pauli exclusion principles, right? They cannot get too close. So if they comes too close, then they are going to occupy the same state. So that is a violation of Pauli exclusion principle. But they can come very close when your spins are opposing each other. So this results of this that the electrostatic energy of the system depends on the relative orientation of the spins, right? So the difference in these energies is basically the exchange energy, because when come close, you have this electrostatic energy as well as this spin orientation energy. So if you have this bunch of spins, suppose I want to calculate the interaction energy on the ion J due to all the other ions, so other spins. So we are talking about interaction energy, interaction on atom spin Sj due to all the spins surrounding that Sj. Then you can calculate this one as this I is all the spins except J, right? So then you have this Je, that's the coupling constant. So you can write this way. So the sum is over all the atoms except the jth atom doesn't interact with itself. So then also we know for the jth atom, your magnetic moment is given by this equation. So G is 2 here, right? So if you plug in that number here, you get this equation for you. You can see negative cancel each other. That's why you need to have J to be positive if you want to have the ferromagnetism, right? So then this equation become this one. So instead of Sj, now we have mu. So this now you can see this is basically interaction of this magnetic moment of that Sj with some, we can think this one as the Weiss field, right? So because interaction energy is mu dot B. So then you can think about exchange interaction has been replaced by the interaction between this dipole with the Weiss field. You can think this whole thing as the Weiss field. So now if this system is in a magnetic field, so if you have external magnetic field, applied magnetic field, then you can calculate the local field as that exchange, the applied field minus that Weiss field. So that we, if you do this one again, actually this summation, if you consider similar spins, so you can consider JE to be constant, say J. So the constant JE. So then if you take this one outside the summation, then this sum of SI becomes same S times your total number of if you have total number of spins here. See. So so B is the applied field. Sum is over all the atoms except the jth one. Jth one is one we are talking about, right? Yeah, J only excludes C nearest neighbors. Yeah, C is the number of. Mostly we are talking about not all the spins, mostly at least nearest neighbor interaction. So C is the nearest number of nearest neighbors. So then also that is mu we are talking about. So now if you want to calculate the magnetization, then you have to multiply by the number of atoms per unit volume. So if you do that one, then your M becomes so sorry. So then we can substitute this term. So you can write M is n times mu, but mu is given by this equation here. You have, if you can come here, this mu is right here. So if you substitute there, you get your M as, and yeah, then the effective exchange field, that BE. So this is your BE, right? So that you can write in terms of your magnetic momentum. So that is given by this expression here. So this is basically your BE, the exchange field. So then the Curie constant, the lambda is given by this J divided by, because that is except for the M, right? If you divide by M, you get this JE divided by mu 0 Ng squared mu B squared, because you remember how to calculate the susceptibility from external magnetic field. So now if you can do a couple of examples. So use the experimental value of the Curie temperature to estimate the Heisenberg exchange integral term. That's we are talking about calculating lambda or your J value. So that's the exchange integral form, right? The concentration of iron atoms, that is N, is given as 8.5 times 10 to 28. So then it has 12 nearest neighbor. That C is 12. So how do you do this one? Your Curie temperature, we know that Tc is given as 1043 Kelvin. So in this case, we know G is 2, but we assume S to be 1 because you have spin up to this. If you consider iron, so you have 2 F electrons. So that's, you have spin half and half, that's 1. So now if you use this equation for lambda, so 3 kBT Te divided by this one, you have all these values. TQ is given here. S is 1, so that means this term becomes 2, right? So that's 2 squared. We have all other things. So if you do that one, lambda is 588. If you know lambda, then you can easily calculate your this exchange interaction JE, that is given by this equation here. If you apply that one, that is this energy unit, right? That is about 1 milli-electron volt. That is the exchange interaction energy, or constant. That's the energy term. So now one important thing of ferromagnet is the hysteresis. Remember, if we had the magnetization, that function of H, if you had the paramagnet, remember it was just linear relationship, right? Just you have straight line. If we have diamagnet, it is negative constant like that. But in ferromagnets, if I apply magnetic field in the forward direction, so it actually shows a little bit like at the smaller fields, they are more like paramagnet, but then it becomes nonlinear and becomes saturated here. So important thing is now when I sweep the magnetic field back, so still in the same direction, I'm decreasing the magnetic field. If it is the paramagnet, it will come back on that straight line. But in the ferromagnet, when I decrease the magnetic field to 0, so it doesn't come back to 0. It has a finite magnetization even at 0 magnetic field. So now I'm going to change the direction of magnetic field. So then I am in the negative magnetic field, I am going to increase from 0. So then you will find this kind of curve. Then here at this field, your magnetization becomes 0, right? So this is y is 0 at this point. So that means this becomes non-magnetic. So we call this is a demagnetization, right? At this point, you can demagnetize the magnets. This is applying a negative magnetic field. So now in the negative direction, I keep increasing until it becomes saturated at a negative magnetization number. Now I am going to increase in this in the negative direction up to here. So then again I am going to switch the direction of the magnetic field, the positive direction. Then I am going to increase it positively. So then it will get back to that original point here. So it will never get back to this 0 magnetic moment for 0 field. That's why we call it a ferromagnet, right? This is very important thing. Like you can see, so when it goes to some value, it at this point it remembers. There's a memory of this magnetization, right? So this will help you to write some information as data storage. Then you can retrieve that information by sweeping magnetic field other way. So we call this one as the remnant magnetization. That means you have even at 0 field, you have this magnetization. So this magnetic field, that is where you make your magnetization 0. That is called the coercivity. So we can easily understand why this is happening. So at the beginning, you have this or randomized spins here, even in all the domains. But when you increase the magnetic field, so all these then these magnetic moments are going to gradually align along the magnetic field. At very high magnetic field, they all are going to be aligned in one direction. That's why you have this saturation. There's nothing else you can do, right? So now again, when you sweep back, so at this point again, you will have your this random magnetic moment. That's why you have 0 magnetization. So then again, when you sweep negatively to the highest value, they all are going to align in the opposite direction. To this here we have magnetization all in positive direction. Now they all line negative direction. So completely magnetized. So then again, when you go back again, it will become non-magnetic. So then again it's going to, so it will go through this loop. 1, 3. So the hysteresis loop shows the history dependent nature of magnetization. So once the material has been driven to saturation, the magnetizing field can then be dropped to 0 and the material will retain most of its magnetization. That means it remembers its history. So that's what we call it, can be used to store information, because that remembers, it has the memory to store that information. So next we'll talk about the ferrimagnets and antiferromagnetism. Ions in most ferrimagnets and antiferromagnets are positioned in two sublattices. You can see in this crystal lattice, you can consider they have two sublattices. So in one sublattice, you have one kind of atoms. So in the other sublattice, you have different kind of atoms. But in one sublattice, all the spins are in one direction, and in the other sublattice, all the spins are in the opposite direction. Here you can see gadolinium cobalt. So you can see gadolinium ions in blue and cobalt ion in green. So this all the gadoliniums have spins in the positive Z direction, and the cobalt spins are all in the negative Z direction. Also, since they are two different materials, they have different magnitude of spin strength, right? So actually, gadolinium has higher value. So that's why they have anti-ferromagnetism. Sorry, ferrimagnetism. So you can understand this one if you take this example of magnetite. So that's a Fe3O4 crystals. So this is a spinel structure. Spinel structure is something they have like AB2X4 kind of structure. So here actually this is instead of AB2 they have A3. So O4, that's a similar structure, but this is usually called inverse this spinel structure. So if you look at this spinel structure, what you have is this, you have these iron atoms, so these red ones. So actually they have, so some these iron atoms, they have oxygen atoms in this tetragonal coordination. So you can see each red, the iron we call is A site. So they have 4 oxygen atoms surrounding that iron. So we call this a tetrahedral site, so or called A site. So then you have this yellow iron atoms. They are surrounded by the 6 atoms. So this is more like octahedral site. So they have two kind of iron atoms, one with tetrahedral sides and other with octahedral. Tetrahedral means you have 4 surrounding oxygen atoms. Here you have 6 surrounding oxygen atoms. So that's what we call tetrahedral sites and the octahedral sites. So the tetrahedral and octahedral sites form the two that sublattices. So like we talked about that one. So then they have spins in two opposite directions. So that's why we have this ferrimagnetism. If you take this one in more details, you can think, yeah, here I show that iron atoms, the tetrahedral iron atoms with 4 oxygen atoms, and here octahedral iron with 6 oxygen atoms. So if you consider this iron, typically iron has this electron configuration, right? Going from 1s2. So then we know after 4s2 actually it start filling 3d orbitals, right? So this this transition metal. So but when you lose electrons, when iron becomes ionized, so they lose this s electrons first, right? So that's why if you take iron, they have these 2 iron structures. So like Fe3O4, you can write as Fe3 plus, Fe2 plus, then Fe3 plus O4. So that is, this is your A site. So this is your B site, because that's why you have 4 oxygen and 6 oxygen surrounding those ions. So since this iron has this 3d6, this an atom, but if you get Fe2 structure, that is this one, Fe2 plus means you lose only one electron. So that you are losing, sorry, 2 electrons, you are losing 2 electrons, but those are 4s2 electrons. That means still you have all 6d electrons. So that's why we have 1, 2, 3, 4, 5, 6, all 6 d electrons are here. But if you have Fe3 plus, 3 plus means you are losing 3 electrons. So that you will lose 2 from here and you lose 1 d electron, that leaving only 5 d electrons. So that means 3 plus has only 5. 1, 2, 3, 4, 5. You lose 1 electron. So now if you take that other Fe3, so that one also has 5 d electrons. Now the exchange interaction means, so you will have this the direct exchange between these two ions, because this has only 5, this has 6. So then you can interact this spin with this one. That's the direct exchange interaction. Or these this d5 and d6, these spins can interact with this another 3 5 that has this this is another sublattice, right? So they can interact with these through this oxygen atom. That's we call the super exchange interaction. So that's how you get this ferromagnetic effect. So here you can see how they are interacting. So this is the direct this double exchange. So then also they can have interaction through this oxygen atom, super exchange interaction. So now if you talk a little bit about this Heisenberg model, suppose you have, like here actually I write x instead of j, that coupling constant. So again, if x is positive, that's a ferromagnet. Suppose if you have just 2 spins, s1, s2, just like hydrogen atom, right? You have 2 hydrogen, if you have a hydrogen molecule with 2 hydrogen atoms, so they both have like a spin 1 and 2. So you can write your total spin as s1 plus s2, right? So just only 2 spins. So then how do you get the total s? You can have 2 ways, right? One is you can have both opposite. So that means your total s will be 0, or you can have both upwards, you get 1. So then also you can have this linear combinations. So to get 1. So that means you will have 1 singlet and this triplet that has spin, total spin 1. So now if you want to calculate the expectation values, so we need to calculate the this spin interaction, this S1 dot S2. That's what we are interested in, right? So, but we know how to calculate S1, S2. If you take S is S1 plus S2, right? So if you square this one, you get squared plus S1 squared plus 2S1 S2 but S2 squared. That means your S1 dot S2 is basically half of this S squared minus S1 squared minus S2 squared, right? So that's what we are interested in, calculating S1 dot S2. So, but we know S can be either. So this capital S squared is basically 1 or 0. So if you take triplet state, so then your S1 dot S2 we can calculate as, for that still we need to know what is the expected value of S1 squared and S2 squared. What is the expectation value of S1 squared or S1 S2 squared is, if you remember, squared is given by S plus 1, right? So that's the eigenvalue of your S squared. So remember, the SC has M times H cross, but S squared has S times S plus 1. So that means SC is half, then S plus 1, this one. So if you add, that is 3 or 4. That is for both S1 squared and S2 squared. So, but we are interested in calculating this one. So that will be S squared. If I calculate for triplet, how do you calculate that? So then S squared. So S squared will be triplet is 1, right? 1 minus S1 squared, that is 3 over 4, then S2 squared 3 over 4. So then if you divide by 2, so you get S1 dot S2 is half. But if you take the singlet state, so then your S squared is 0, right? So this S squared is 0. Then minus you have S1 squared, this is 3 over 4, minus 3 over 4, that is minus, yeah, then you have to divide by 2, then you get minus 3 over 4. That's how you calculate your this cross term, right? S1 dot S2 from this equation. So now if you want to calculate this Hamiltonian for all the spins, so that means I need to calculate all this cross terms. So that means I have to get Si dot Sj for a given Sj, I have to calculate for all I, so except for j, then I have to calculate for all the j values, right? So that's how you calculate the total interaction of each pair. So then if I have external magnetic field, so then I need to get this mu dot s, right? But s is sum of all si values. This is mu dot s. This is all the interaction terms. That's very easy to calculate. So, but if you only consider nearest neighbors, so then you can take this xij as a constant. That's a ferromagnet is a positive number. So then you have to sum over only the nearest neighbor n for this your Sn. So what you have to sum over all the spins I. So then this is basically yeah, this term here. So you can keep changing this one. So then if you use some mean field approximation, you can actually take this sum over Si as a common term. Then this becomes this sum over nxs. Then you get this also this term Ge mu b b0. So you can write this one very easy. Then you can write this one as again this sum over nn. So if this is constant term, this average S value. So then you can take x out and you get total number of nn terms, right? So this number of nearest neighbors on this one. You just take this one out of the summation term. Then you can write it this way. So now we know how to, if you calculate the magnetization is given by total magnetic moment, that is remember Ge S magnetic moment is given as Ge times your mu b times S, right? So then if you have total number of spins n, so to get the magnetization you have to find the total number of dipoles per unit volume. So if you do this one, you will substitute this S value. So here you can write in terms of m and n. So then if you plug in here, you get this expression. So this one I can write as sum over Si dot, so this B0, then I write this whole thing as BW. That's more like the Weiss field, right? So now you can see how you get to this local magnetic field, the Weiss field. So that means the BW is this whole thing here, right? So the BW is expressed as this BE m times this whole value. So this is what we are here. So now, so if you want to calculate the total magnetic moment, so we have to use that Boltzmann distribution. So we just calculate magnetic moment here times your this Maxwell-Boltzmann weighting factor E over kBt. This is your magnetic moment. We did one before when you came up with that brilliant function, right? But here in this case, you have to evaluate mj from this minus j to j. But for we assume in this case j to be half, like in the case of iron. So that means mj goes from only minus half to plus half for an easy example. So that means you have only two terms here, right? You just substitute mj as minus half and plus half. That means you have one term e minus half, then plus e plus half. So that means you have some exponential function, right? If you do that one, you get your, so after mu c, you can calculate mt just by multiplying by n and divide by v. Then you get this function. X means this whole thing inside here. So this is nothing but the tan function. So this magnetization as a function of temperature is given as a tan of x. So x is the function of both Weiss field and the temperature term here. So then if you calculate m, if you normalize for t equals 0, so this is, you can write in this fashion. So this theta c is this nearest neighbor, number of nearest neighbors times your exchange interaction constant, and this 2 squared over kb. So actually that function people have measured this magnetization for different temperatures. Then if you can normalize to your Curie temperature, so you can see data for all these three, iron, cobalt, and nickel. They all follow this the theoretical curve coming from this equation. That follows very well this theory. Okay, so then also we talk about this Curie temperature for ferromagnetic susceptibility C over T over theta C. This theta C, now we know how to calculate in terms of exchange interaction. So if you look at most of the ferromagnets, actually they are in the this transition metals, and few in the this rare earths. So these are very common ferromagnets, but there are many alloys or that becomes ferromagnets, mostly alignment of spin magnetic moments. So finally, I want to a little bit about the ferromagnetic domains. So if you take a ferromagnet, these are the domains we are talking about, right? Inside each domain, you have these magnetic preferential directions. Now, if I apply magnetic field, actually these are called the domain walls. So here, this is domain walls. So then through these domain walls, actually spins are kind of reorienting in a narrow distance. So this is called the block walls. So you can image these domains using some magneto scanning probe techniques. So you can see these spins are reorienting at the, so here it's coming like this near the domain wall, it's reorienting. So then again, it's reorienting at the domain wall. So then it becomes like this. You can see this reorienting of spins at the domain walls. So then also, if you have this is like this magnetic domains without external magnetic field, but if you apply a magnetic field, you will see this moving of these domain walls. So initially domain wall was here. So now you can see domain wall is moving. So there's a domain wall movement here. So then we talked about this hysteresis. So you can see, so typically you have this relationship, right? If you have paramagnetic situation, your mu 0 m equals chi m b0, right? Because m is given by b0. So that's the external field times this one. But when that is the situation, you have this linear curve. So then it comes back linearly. But for ferromagnets, that's not equal, right? So that's why you have this non-linear behavior even in this range. It's not equal. So then finally, so these ferromagnets can be used in many applications, mostly hard magnets. So these are basically the permanent magnets, right? They have many applications. Then, but the soft magnets, they are mostly used for like this transformer core material and in motors, so that when the magnetization needs to be changed. So in hard magnets, your magnetization cannot be easily changed. So the hard magnets is defined as the size of your curve. So you can see in this range you have very high remnant field and also very high cohesivity. But if you have soft magnet, that loop is very narrow. So your remnant magnetization and the cohesivity are very small. So that is actually given by the area of this one, that is B dot DH or M dot DH. So that's the defines whether it's a hard magnet or soft magnet. Okay, so that's all. So I'm going to stop here. So that's the end of our 3 lectures on magnetism. Thank you.